Think about a self-driving car having to slam on its brakes, or a drone trying to map a raging wildfire. These systems are making split-second, sometimes life-or-death decisions with incomplete information. So today, we're going to dig into the incredible algorithms that are designed to navigate all that uncertainty. Let's dive in.
And yeah, the stakes could not be higher. We are not talking about an algorithm recommending a movie you might like. No, no. Think about aircraft collision avoidance systems or coordinating disaster response. These are scenarios where an automated system absolutely has to make the right call, right now. So how on earth do they do it? Let's imagine an autonomous drone flying over a huge wildfire. Its main job is to figure out where to look next to give firefighters the most useful information possible. But, it can't be everywhere at once, and the fire itself is totally unpredictable. This is the core challenge right here. To really get how that drone makes a choice, we need to think of it as an agent. Now, the agent is just the algorithm, the brain, the decision maker. Everything else, the fire, the wind, the mountains, you name it, that's the environment. The whole process is basically a continuous back and forth, a conversation between these two. And this interaction follows a really simple but incredibly powerful loop. So first, the drone observes its surroundings. Step 2, it chooses an action, like, okay, I'm gonna fly east. Then step 3, that action changes its perspective on the world. And finally, the loop starts all over again. This whole thing just repeats, constantly updating its understanding, thousands of times a second. But here's the catch. That decision loop has a massive vulnerability: imperfect information. Smoke can block a camera, a sensor can give a weird reading. The drone is never ever 100% certain about what's happening. And this is the moment where algorithms have to make a huge shift, from thinking in absolutes to thinking in probabilities. And that leads us to the crucial question, right? If a machine can't be certain, how can it possibly make a rational decision? It can't just rely on simple true or false logic. It needs a way to handle all those gray areas. Well, the solution is to represent that uncertainty with math. The system stops saying, the fire is here. Instead, it starts thinking, there's an 80% chance it's here, and maybe a 20% chance it's over there. This whole idea of using degrees of belief is really the bedrock of modern algorithmic reasoning. So how do you keep all these probabilities organized? Well, algorithms use this incredibly powerful tool called a Bayesian network. You can think of it like a map of cause and effect. It connects all these different variables to show how a change in one thing affects the likelihood of another. Let's make this a little more concrete. Imagine we're monitoring a satellite. An electrical failure could be caused by a bad battery, or maybe a faulty solar panel. The effects we might actually see are the satellite's path changing slightly, or maybe we just lose communication. A Bayesian network connects all these dots, linking the potential causes to their observable effects. And this leads to this really cool reasoning concept called explaining away. Okay, so initially, if we see the electrical system failed, we might suspect both the battery and the solar panel. But then, what if we get new data showing the battery is perfectly fine? Suddenly, our belief that the solar panel is the culprit shoots way, way up. The good battery explains away one possibility, which makes the other one far more likely. It's a real aha moment for the algorithm. Okay, so being able to weigh the odds is one thing. That's huge. But how does an algorithm know what it's even trying to achieve? It needs a goal, right? A clear definition of what a good outcome actually is. This is where something called utility theory comes in. It's basically a scorecard for the future. We, the human designers, assign a numerical score, we call it utility, to every single possible outcome. The algorithm's goal then becomes super simple. Just take actions that get the highest possible score over time. And this simple example with a puppy makes it crystal clear. Not feeding a hungry puppy, that's the worst possible outcome. A utility score of -1. Very bad. Feeding a puppy that isn't even hungry, well, that's a bit wasteful, so we'll give it a -0.5. Feeding a hungry puppy? Great. That's a good outcome, only -0.1. And doing nothing when the puppy isn't hungry, that's our baseline. A neutral 0. The algorithm will now just choose the action that leads to the best possible score. Now, compare that cold, hard logic with how our own brains work. We are so susceptible to something called the framing effect. Research shows that we make totally different choices based on whether a problem is framed in terms of gains or losses, even if the outcomes are identical. An algorithm guided by utility theory doesn't have this bias. It just crunches the numbers. All right, so we've got a system that can weigh probabilities and score outcomes to make the best decision right now. But the real magic, the part that's truly amazing, happens when it learns from experience to make even better decisions tomorrow. And there are two main ways this happens. In something called planning, the algorithm has a perfect model of the world. It's like having a complete map before you start a road trip. But in most real-world problems, we don't have that perfect map. And that's where reinforcement learning comes in. The agent is basically dropped into the environment with no instructions and has to learn purely through trial and error, guided by a system of rewards and penalties. And this leads to a classic, fascinating dilemma. Should the agent exploit a strategy that it already knows works pretty well? Or should it explore a totally new, maybe risky, action that could lead to an even bigger reward? Balancing this trade-off between exploration and exploitation is one of the hardest and most interesting parts of reinforcement learning. So, how does all of this come together in the real world? Because these decision-making systems aren't just stuck in a lab somewhere, they are actively out there, shaping our world right now. I mean, their impact is absolutely massive. In medicine, they're helping doctors diagnose diseases earlier and finding better matches for organ donors. They're making our energy grid smarter and even helping to protect endangered species from poachers. They're optimizing traffic in our cities and making autonomous cars and airplanes safer. The potential for good is just incredible. But of course, with all this power comes huge responsibility. The same optimization that delivers a package faster can also be used to spread misinformation. Biased training data will lead to biased, unfair decisions. And maybe most critically, we have to make sure the goals we set, those utility scores, don't create harmful, unintended consequences. That is the core of what we call the alignment problem. And that leaves us with what might be the most important question of all. As we hand over more and more responsibility to these incredibly powerful systems, we have to get their goals, their utility functions, exactly right. Because in the end, the most important decisions these algorithms make will be the ones we programmed into them in the first place.